So today we are going to discuss about FIR filter design. In the previous lecture we discussed IIR filter design and different methods of IIR filter design like IIT method, bilinear transformation method, and we also solved some numerical example using BLT and IIT method. Now in this class we basically discuss about FIR filter design process. Now, before going to discuss FIR filter design, we have to know that what is the speciality of FIR filter. Means what can I get extra from FIR filter? What is the difference with IIR one? Now, as the name suggests, IIR means it gives infinite impulse response. Means if we plot the HN, impulse response of this filter of the system, and it will be from minus infinity to plus infinity. Now, in case of FIR, it will be some from N1 to N2 or minus N1 to plus N1 like that. So it will be finite. Impulse response will be finite. And one main advantage or difference I can say is FIR by FIR system we can design exact linear phase system. So in communication, this linear phase system is very important. Okay, so if we design exact linear phase system, then the reception of the signal at the receiver will be very faithful. So the linear phase response is very important. Okay, so this linear phase system can be implemented by FIR filter. Now, what is the linear phase actually? This equation basically defines this h e to the power j omega is basically a transfer function of a LTI discrete time system, and whose impulse response is h of n. Okay. Now this can be written as its magnitude response and its phase response. Now this magnitude response, if I say normally that if this phase response, if this phase response is 0, then it will be a zero phase system. Means it will not affect if a signal is passed through this kind of system with zero phase. The output signal will not be output phase of the signal will not be affected by the phase response of the system. So that is why this kind of system is called zero phase system. Now this kind of system is ideal in nature. Now if in any system, if the signal passes from input to output, the output phase also changes. So if the change is linear, then we can predict that how much change it will be, how much change it will turn to the output. So in a linear phase, this line is very important, that this theta omega is proportional to the frequency omega, then the transfer function is known as the linear phase. So if the phase response changes linearly, then we can say this kind of system as a linear phase system. Now in case of linear phase system, we can write down the overall frequency response like that, where we consider the magnitude as a 1. Okay, means this mod h e to the power j omega is we consider as a 1. So this is basically, this alpha is basically the constant, and I can say this is the phase response, linear phase. Okay, so this is the concept of a linear phase system, and if we can also show that in case of IIR filter, this kind of linear phase system is not possible. Okay, now we can show you that this is the condition of the linear phase. Okay, this is the condition of this, the theta omega is equal to minus alpha omega. The same thing, that this phase response, this theta omega is the phase response, is linearly proportional with this omega, where omega is basically minus pi to pi. Now if phase response is linear, then if we calculate the phase delay or the group delay, both will be constant, because we know that the formula of the phase delay is this and formula of the group delay is this. So if we can find out tau p and tau g, both will be constant. Okay. So if the for a linear phase FIR filter, both phase delay and group delay is constant. Now I can show you also by the help of a MATLAB design that here this is a filter design tool, FDA toolbox, where I have implemented a FIR filter, where I have implemented FIR filter, low pass FIR filter. See, this is a low pass design. So we choose a low pass design, and then there are different kind of filter, equiripple, window based. If I check any window, there are different methods actually. So if you any window, then the order should be minimum, and if I use a rectangular window or flat top, any window you can select from this. Okay, suppose we select a rectangular window, and the sampling frequency and cutoff frequency is predefined sampling frequency. If we design this filter, you can see that yes, you can see that. So this is the pass band. This is the pass band. Okay, so in this pass band, the phase is exactly linear. Okay, so this is the magnitude response. The blue line is basically magnitude response, and the orange line is basically phase response. So within the pass band, the phase response is exactly linear. So that is the meaning of the linear phase. Now, if I implement the same thing with the IIR one, so we can select a IIR one, this IIR Waterworth. So we will design this Waterworth filter, and if we again design the same filter using IIR, we can see, yes, we can see within the pass band. So this is the pass band. Within the pass band, this frequency response is not linear. It's a non-linear in nature. So that is a practical implementation which you can implement in using MATLAB. This is a very well-defined tool. Filter designer toolbox is available. So this by this you can see that that IIR filter cannot provide you a linear phase response. So that is why to get a linear phase response, we have to opt for FIR filter. Now mathematically you also can prove that why IIR filter is not capable of producing linear phase. Okay, so we'll go switch to the this PDF. Yes. So what are the characteristics? So before we go, this is the causal filter, transfer function of the causal filter. Why it is causal? Because it is valid from 0 to n minus 1. So it's a finite duration. Obviously, h of z is finite duration. It is h of n is the impulse response. And if we calculate the h omega, that means if we calculate the DTFT of that, so if we do the Fourier transform of this, DTFT means if we take the Fourier transform, we will get this equation h omega. This is very simple, and we know that the Fourier transform is periodic in nature. So by this equation we can show that, and this h omega is basically nothing but this is the magnitude response, and this is the phase response. So if we consider this magnitude response as a 1, but this phase response, theta omega, is linearly proportional. So this is the line where we will assign that the phase response is linear. If the phase response is linear, as we discussed in the previous little bit earlier, that the phase delay and group delay will be constant. So if the phase delay and group delay are constant, means it is alpha. It's very simple. You can do that. So for a linear phase system, FIR system, if the phase delay or group delay is constant, then we can write down. That's see, if we write down, we can write down this equation. This is nothing but what? This is h of omega. Okay, this is basically h of omega. This one. See, this is basically h of omega. So h of omega, this can be written as a magnitude response and phase response. Now, if we apply the Euler formula, that is e to the power minus j theta, this is, so we can write down cos theta minus j sin theta, and this is basically e to the power j theta is cos theta plus j sin theta, and if we segregate the real part and imaginary part, we will get these two equations. And if we divide that two, and if we rearrange this equation, we will get this formula. Okay, here you have to just apply a trigonometric formula. I will show you in details that what you have to do exactly. In the book there is a step jump given. Okay, so these things I already provided you this lecture notes. Please go through that. So just apply this formula, sin A minus B, and you can land it to this equation. Okay, so detailed calculation is already I have given to you. Now, so this is the equation. This equation is true if, this is very important, if the impulse response is if the impulse response follow this rule. That means if the impulse response is symmetric and the center of symmetricity is this. Now, as I said that in FIR the impulse response are finite, so it will be from suppose 0 to n minus 1 or any finite response. So this finite impulse response, if I draw here, suppose if I draw for n equal to 8, that is capital N is basically 8. So what is that basically? So capital N is equal to 8 means 0 to capital N is equal to 9 means there are total from 0 to 8. If we draw that, the center of symmetricity is 4. Okay, and we can say that this sample is exactly symmetric with this. This sample is exactly symmetric with this. This sample is exactly symmetric with this, and this sample is exactly symmetric with this. So this property and the center of symmetricity is 4, which is nothing but, in generally we can say this. In case this n is 9, so 9 minus 1 8, 8 by 2, so alpha is 4. So the center of symmetricity is 4. So if what we can conclude that if the system is linear phase and if the system is linear phase and obviously if the phase delay and group delay is constant, then we can say that the FIR filter is symmetric about a point, and this center of symmetricity is defined by this rule, alpha is equal to n minus 1 by 2. Now this capital N is basically length of the filter. Okay, length of the FIR filter. So this line is the impulse response satisfying the symmetry condition for odd and even value. So this capital N can be even and odd. So if we take n equal to 9, the center of symmetricity is 4th sample, and when n equal to 8, the center of symmetricity is 3.5. So this is basically, so here the length of the filter can be even and odd, and this is the impulse response can be symmetric about this axis. Okay, so this is a one kind of filter where the length is even or odd and the frequency impulse response is symmetric about the axis. Now there are another kind of FIR linear phase filter where the impulse response is asymmetric about a point, and again the length of the filter can be even and odd. So there are 4 kind of filters. This is called type 1, where I assume that the length of the filter is even or odd. So if I say n equal to even, and so there are 4 total response can be possible. I will show you. Yes, this one. Sorry. Yeah. So this one. The second one is this center of this is asymmetric. This is type 2 filter. So there are total 4 types of FIR filter where the center of symmetricity center of symmetricity is not. The impulse response can be symmetric about axis, and asymmetric about axis, and the length can be even and odd. So total of 4 combinations is possible. So symmetric even, symmetric odd, asymmetric even, and asymmetric odd. So these are the 4 types of filter, linear phase FIR filter is possible. In this first discussion, we have discussed the first type, or type 1 filter, where I'll show you that yes, this is. So if the symmetrical impulse response and n is odd, this is type 1. Symmetrical impulse response, n is even, type 2. Asymmetric impulse response, n is odd. Asymmetric impulse response, n is even. So we already discussed the symmetric impulse response. Now what is asymmetric? As in asymmetric case, we will say if the constant group delay is the requirement, not the phase delay. Means in the previous case what I said, that theta omega is equal to minus alpha omega. So this beta is not there, minus alpha omega. In that case, the group delay and phase delay both are constant. Now if the constant group delay is our requirement, but the phase delay can vary. So this is the equation. If I apply this equation, and again we will do all the same things what we have done previously, we will land it to this equation. And you can say that this equation is true if the impulse response is anti-symmetric. This negative sign is the indication of anti-symmetricity. Anti-symmetricity means this one. So this response is exactly equal to this response, but it is in anti-symmetric, it is reverse. Similarly, this response is exactly equal to this response, but it is anti-symmetric. Similarly, this one and this one. So we also have a center of symmetricity. If n is odd, then center of symmetricity will be is 4 here. If n is odd, that means if we consider n equal to 9. Now if n is 8, then the center of symmetry is 3.5. Okay. So in both the cases, for symmetric impulse response and asymmetric impulse response, in both the cases the phase response will be linear. Okay. So there are total 4 types of filters. Okay. Now in this previous design, in the previous discussion, we said that this equation is true if the filter response is symmetric, or this equation is true if the filter response is anti-symmetric. Now we can prove this with the help of an example. Okay, we can prove this with the help of an example. See, if we consider the length is 7, and if this filter has a linear phase, so that this is equal to 0. Okay, so length is 7 means capital N is 7. So the center of symmetricity is 3. So basically consider like this. Okay, so total filter response, the length is so this is 3, 6, 7. Okay, so these are the impulse responses, and the center of symmetricity is 0, 1, 2, 3. This is 3. Okay, and this is 0, and this is 6, 3, 4, 5, 6. Okay, so in case of symmetricity, that means this H0 is equal to H of 6, H of 1 is equal to H of 5. So symmetricity means this one, H0 is equal to H of 6, H1 is equal to H of 5, H2 is equal to H of 4, and H3 is the center of symmetricity. Okay, now in this equation, we have to prove that if the FIR filter having the length 7, and if it is a linear phase, then this equation is 0. So simply what we will do, we'll put n equal to 6 here. So, and we will expand this summation. If we expand this summation, we will get this equation. This is very easy. Okay, since we know alpha is equal to 3, so this is the case. Now we know that h of 0 is equal to h of 6, okay, from the properties of symmetricity. So if we consider that FIR response is symmetric, then if we apply the symmetricity property, it will goes to 0. Simply it will goes to 0 because h of 0 is equal to h of 6. So these two will be cancelled out because sine of minus theta is equal to minus sine theta. So this negative sign will come out, and if I put h6 in spite of h0, so this first term will be cancelled out. Similarly, this term will cancel out with h of 5. Okay, this term will cancel out with h of 4, and this is the center of symmetricity where sine 0 is 0. So overall, ultimately it is 0. So what is the result? So this is 0 proved. So here we proved in reverse way, that we take that we assume that filter response is this is a linear phase system and it is symmetric about axis. If this condition is true, then this equation is true. But here what we did, here we said that this is true, then this equation will be true if the filter response is symmetric. So we prove these things in both ways. Okay, so what is the conclusion of this discussion is that this FIR filter will be a linear phase system, and if it is a linear phase, then its impulse response is obviously symmetric or antisymmetric, and the length of the filter can be even and odd. So depending on these combinations, we have total 4 kind of filters: symmetric, even, symmetric, odd, asymmetric, even, and asymmetric, odd. Okay, so these are the basic discussion where and one more thing in IIR design we cannot implement a linear phase system because IIR filter, these impulse responses are infinite in nature. Infinite in nature means, I can show you here. This is the impulse response, suppose. So this length is from 0 to 7. So we can define this length. Okay, this is a finite length. Now infinite means the impulse responses are infinite. It starts from minus infinity to goes plus infinity. So we cannot say that what is the point of symmetricity. So unless otherwise we cannot say that this impulse response is symmetric, the phase response cannot be linear. So since in case of IIR filter, the impulse response are infinite nature, it starts from minus infinity to plus infinity, goes to plus infinity. We cannot define the center of symmetricity, and we also cannot define that that IIR filter will gives you a linear phase system. Okay, so that is the reason from the IIR filter we cannot implement a linear phase system. I also show you through this implementation of MATLAB where this IIR filter gives you a non-linear response in passband. Okay, so this is the just basics of FIR filter. In the next class we will discuss different design method of FIR filter, window method, frequency sampling method. Okay, so for that this is the class for today. Please listen this lecture, and if you have and the next class we will discuss FIR filter using windowing method. Thank you for listening to the class.